Hello and welcome to a more thorough explanation of the principles involved with solubility product, or KSP. So today we're going to talk about sort of three extensions of the KSP idea. So we're going to talk, as mentioned in the previous video, about the common ion effect and how that affects KSP. And then we're going to talk a little bit about whether you can predict, spoiler alert, you can, whether mixtures will form precipitates or not. And then we're also going to talk about the non-one-to-one ion ratios. So those are the three topics for today's video. I would make sure that you've watched the previous one or have a pre-existing understanding of KSP so that you know a little bit more about it. So moving right along. The first thing I want to talk about then is this idea of the common ion effect and how that plays a role. So again, the common ion effect being that if more than one substance is a source of a particular ion, refer to that as a common ion. And it has, according to Le Chatelier's principle, an impact on the position of equilibrium as a result. So if you recall, we were talking about calcium carbonate yesterday. So if we just briefly revisit calcium carbonate, remember that it was in equilibrium with calcium 2 plus and CO3 2 minus carbonate. And at 25 Celsius, KSP, which equals those two molarities times one another, also happened to equal 3.3 times 10 to the negative ninth. And remember that in a solution of just calcium carbonate in water, the two ions have to be equal in molarity. So these two would be equal in their molarity because I get one of each of them every time calcium carbonate breaks up. So they have to be made in equal amounts. You get one of each every time it breaks up. It's like if I broke down 10 bicycles, I would definitely have 10 front wheels and 10 rear wheels. But what if I walked into a room where there were a bunch of pre-existing wheels? There's no guarantee that the front and back wheels would be equal in amount anymore. And that's what the common ion effect is going to sort of work through. So for example, what if we said, I want to know the solubility. In other words, how much calcium carbonate can I dissolve in not just into water, but in a solution that has stuff dissolved in water, specifically a common ion. So let's say that we use 0.010 molar calcium chloride. So now we're going to have a situation where the common ion that we're going to talk about here would be the calcium 2 plus that we have here and also here. So rather than adding it to water where there is no pre-existing calcium, now there is going to be some. And what this ends up looking like, and I'll go to the next slide here, is going to be a rice box type problem. It's probably the easiest way to think about approaching it. But before we do that, remember, let's just keep in mind that the point of reference here, the comparison, is that the solubility in just H2O was right around 5.8 times 10 to the negative fifth molar. So that'll be a value that we compare it to as we go through this. So if we set this up like a rice box, all right, sure that was riveting video making right there. Because this is a solid, we don't have to worry about filling any part of this in. Normally the calcium and the carbonate would both start at 0. They're not going to start at 0 in this case. One will, but one won't, because there is a bunch of calcium in here from the calcium chloride. There is no carbonate though, because it was not the common ion. And because there isn't any calcium yet, its side has to go up, which means the calcium on the same side also goes up, and we're going to say that they both go up by x. So this ends up going up by 0.1 plus x, and this by x. And so again, we go back to our KSP, 3.3 times 10 to the negative ninth will equal 0.10 plus x times x. And again, this plus x part we don't really have to care about, so that's out for the time being, and really for all the problems that we're going to do, which makes the math really quite simple. X is just going to equal 3.3 times 10 to the negative 9th divided by 0.1, so 3.3 times 10 to the negative 8th molar, and that is the molarity of carbonate, but there's one calcium carbonate for every one carbonate, so it's the same value. So 3.3 times 10 to the negative 8th molar calcium carbonate. So the molarity is substantially lower, right? That's far lower than the 5.8 times 10 to the negative 5th we had before. I mean, I guess if you did the math, it's probably 1,400 times smaller. So maybe it's about 1 out of every 1,400 the previous solubility. So the solubility has gotten much, much lower as we've introduced another source of calcium here, a source of calcium that, while not particularly highly concentrated, is substantially higher than the calcium carbonate could ever make on its own. And because there's so much of it, the collisions with carbonate are going to happen very frequently as a result. And because they're happening so frequently, the reaction is going to push back to the left, and we're going to get a lot of solid forming. So you don't get much dissolving when this common ion is present. Just as a related idea to this, before we move on to talk about the predicting of precipitations, you could also have sort of an uncommon ion. I don't know if anyone uses that term, but I'll refer to it that way, which is, what if there's an ion, a pre-existing ion removes one of our compound's ions? So what if a pre-existing ion removes or reacts with one of our ions? So, what if something reacts with either the calcium or the carbonate? And let's think about the carbonate here, for instance. What if we use, what if we put calcium carbonate? We're not going to do the math of this, but what if we put the calcium carbonate into 0.10 molar HCl? So here, what's going to happen is that the H plus that's here reacts with the carbonate. And you may recall that when it reacts with carbonate, bubbles and fizzes, so they become CO2 and H2O as a result. And because they're doing that, they're going to use up CO3 2-. So CO3 2- goes down, and when it goes down, the reaction keeps shifting to the right to put it back. So actually, that causes calcium carbonate to be more soluble. And this was the problem that I mentioned in yesterday's video about acid rain. Acid rain contains a lot of sources of H+, and when those were landing on marble buildings and marble statues, they were causing removal of the carbonate ion from the equilibrium, and so more and more of the solid could dissolve to try to replace that to establish equilibrium. And so very valuable, very historically significant structures were being heavily damaged during this time, and a lot of them were moved inside, although a lot of them suffered permanent damage. There's really no way to undo the dissolving of a piece of marble. So that's certainly a related idea, which is, if I remove the ion from solution, I can make the solid actually more soluble rather than less. All right, our second concept is going to be this idea of predicting precipitation. That is, if I bring two different solutions together, can I determine whether they're going to make a precipitate when I mix them together or not? And so the example then might be, it's kind of a common ion effect, but there's sort of two different ions that we're comparing. So for example, what if equal volumes of 0.10 molar calcium chloride and 0.010 molar sodium carbonate are mixed? Will a PPT, a precipitate of calcium carbonate, form? So what we're really trying to compare here then is, I've got calcium 2+ here, I've got carbonate 2- there. When I bump those two things into each other from two different solutions and they collide, are they going to be colliding often enough to make a solid or not? And so what we can do is simply fall back on our KSP expression, but we're going to use it as QSP, sort of our are we there yet comparison. How many ions do we have? How often are they colliding compared to how often they should be colliding at a situation we know is saturated at the KSP value of the solubility. So an easy sort of thing to do, but the trick here is because we added equal volumes, the molarities are going to drop as a result. So because the volume is doubling for both of these things, the molarity will be cut in half for both of them. So calcium chloride doesn't have any sodium carbonate in it, so when it's mixed, the volume is doubling, but you're not picking up any calcium or chloride ions. So the molarity of calcium chloride is dropping in half, as is the molarity of sodium carbonate. So we really have 0.050 molar calcium chloride and 0.0050 molar Na2CO3. And of course, both of those, I'm really not concerned about the chloride. I'm just worried about the carbonate. I'm not really worried about the sodium. I'm just worried about the carbonate. So we're going to just test QSP. So we're just going to plug them in according to the K expression and say 0.050 times 0.0050 and see what we get. So that's 5 times 10 to the negative second times 5 times 10 to the negative third. So that's 25 times 10 to the negative fifth, or 2.5 times 10 to the negative fourth. So that is substantially higher than 3.3 times 10 to the negative ninth, which is our KSP value. And that much higher value indicates we have a whole lot of ions. So there are many more ions than you would normally get at equilibrium. And since there are many more ions than at equilibrium, they're going to be colliding a lot more often than you get at equilibrium. And because they're colliding a lot more than you get at equilibrium, you're much more likely to get a solid, and indeed you would. So you're going to form a precipitate. So in other words, if QSP is greater than KSP, you get a precipitate. And if QSP is less than KSP, that means you don't have very many ions colliding compared to what you do at equilibrium. You would not get a precipitate. There would still be room to add more ions to get to that situation. So I think a fairly easy concept to apply. You just plug those in to get your comparison with K. All right, one last topic for the day, one last extension of KSP, and that is this concept of what about the non-one-to-one ratios? So what if, for example, we have something like magnesium hydroxide, which we know, or we should know certainly, is not a strong base, it's a weak base. We also know that because of Coulombic attractions, magnesium with a charge of 2+ but a smaller radius is stronger in its attraction to hydroxide than calcium or strontium or barium. And so it's a weak base, and it's a weak base because very little of it dissolves. And the idea of milk of magnesia, it looks milky because it doesn't dissolve very well in water. So you get sort of a slurry of this chalky compound that doesn't dissolve particularly well in water with a little bit of it that does dissolve in water. So MgOH2 is not particularly soluble. So MgOH2 forms a solubility product equilibrium the same way that all these sort of soluble or insoluble compounds do. You get Mg2+ aqueous, but the trick here is that you get 2 hydroxides instead of just 1. And again, remember the effects of that are that not only do you get double the number of hydroxide ions compared to magnesium, but because you have double the number of ions, there's an exponential effect on how often they collide. And so the KSP expression would be the molarity of Mg2+ times the molarity of OH- squared. And then if we went into a rice box situation, which we'll probably talk a little bit about, Mg2+ would be going up by x, OH- would be going up by 2x, and that would mean that I would be plugging in x here and 2x quantity squared there because it's both doubling the molarity and has that exponential effect. And so you would get this 4x cubed situation being equal to KSP. And that's different than the nice easy x squared that you get from 1-to-1 ions. You can also have ions where the ratio is 1-to-3. Then you get a 27x to the fourth situation, and the math gets a little bit crazier. So we can do a quick example problem here and then shut it down for the day. So for instance, KSP at 25 Celsius for magnesium hydroxide is equal to 5.6 times 10 to the negative 12th. And if that would equal the 4x cubed situation that we just described, where x represents mg2 plus, which we'll talk about why that's the case here in just a moment, then if we divide that, you get 1.4 times 10 to the negative 12th equals x cubed. And again, without a calculator, the cube root of that's going to be somewhere around 1, we'll say 0.1, I have no idea. As they say, don't at me, bro, times 10 to the negative 4th molar. And that's Mg2 plus, but there's 1 MgOH2 for every 1 Mg2 plus. So that also equals the molarity of MgOH2. So that's how much you could dissolve in a liter of water, about 1.1 times 10 to the negative 4th moles in a liter. So not particularly soluble, thus the milk of magnesia idea there. A lot of ideas could be introduced and combined here. We could talk about common ion effects. We could talk about pH. For instance, it's not particularly surprising that milk of magnesia is very soluble in acidic solutions because the acid uses up the hydroxide. So if I had an acidic solution, the hydroxide would get used up. And when it gets used up, the reaction would shift more to the right to put it back. And you would therefore get more dissolving of magnesium hydroxide in an acidic solution. So I think that's fairly intuitive. You can imagine it's not particularly soluble in a basic solution. With a basic solution, you would have a lot of hydroxide. And if you have a lot of hydroxide, they collide more often with Mg2 plus, and the reaction would shift back to the left, and you get even less of it dissolving. So you could talk about pH effects here, in addition to sort of just a general presentation of the common ion effect. You could talk about will it make it precipitate with that sort of problem, all sorts of things. But we're not here to worry about that today. So just 3 different extensions of the KSP idea. We'll talk a little bit more about some of these things when we wrap up KSP and maybe look at a video where someone else has done some reactions. I'm not allowed or able to get into the building, so I can't really do some demos for you at the moment. But luckily other people have and have recorded them. So we'll look at some of those tomorrow and talk about those a little bit. All right, have yourselves a good day.